Hi, we will be talking about curves and spline, basically because when we are working with animations, they will have often a time when you will want to encode your animation, and somehow, if you have keyframes, you want to be able to have an interpolation between those keyframes, or you might have an object that have to follow a certain path. So mathematically, we will be using curves, and there are several types of curves, and so I wanted to have those videos to show you the mathematical background behind a few of them. So when we'll be doing white papers, where I will be able to just copy the code from this notebook and reuse them inside of our studies. When we talk about curve and spline, basically we have two types of curves. We have the approximation curves and we have the interpolation curves. Interpolation curves is the one you will want to use, when you encode your animation data as keyframes. You will want to make sure that actually your interpolation goes through all the keyframes you set, and then you have in-betweens computed for you. That's the interpolation curves. In that case, we will study the Hermite curves, and we will have the cardinal spline as it extends. And you have the approximation curves, which is the fact that you don't need your curve to go through every points, but you need to follow the points, the data points as close as possible. And on the approximation curve, we will be using the Bezier curve, which is the most known one. And as it extends, we will be studying the cubic B-spline. So as a first one, we will be studying the Bezier curve. And what the Bezier curve is the most known one in the industry. When we talk about animations, usually is the Bezier curve you encounter the first time. And we will be studying the Bezier curve through the Casteljau algorithm. And first, before going in through the mathematics and all that kind of stuff, what I will do is that I will actually show you what it is and how it works, and then we could see what is the mathematical formula for it. So a Bezier curve can be computed with any number of points. The only important part is that to know that the Bezier curve is parameterized by a t-value usually that goes between 0 and 1. And the idea is that at time 0, you are at the position of your first point, and at t1, you will be at the position of your last point. So if I draw the Bezier curve for the simple case of a quadratic one, what you have is we start at the first point, we end at the last point, and we have the curve that goes towards the point in between. And how the Casteljau algorithm compute this, it's basically by a bunch of linear interpolation. So what you do is that you take the linear interpolation of the point 1 and 2 that give you that yellow one, and you do the same with point 2 and 3, and that give you that red one. And now that you have those 2 points, you again do the linear interpolation between those 2 points, and that give you the point on the Bezier curve. And between 0 and 1, it draw the entire Bezier curve this way. And it works with any degrees. So in this case, I've showed you with the quadratic one. If I go cubic, so with the 4 points, it is the same concept, except that you have more steps, of course. You do an interpolation between the first and second, the second and third, the third and fourth, and so on, and you repeat every time. And it works for any number of bones, as I said, any number of points, as I said. And the mathematical formula for it is a recursive function. It basically says that a Bezier curve that has only one point is equal to that point. That's it. And any other Bezier curve that is defined with, in this case, n points, is just equal to the linear interpolation with the Bezier curve that goes from point 0 to point n minus 1. And the Bezier curve that goes from point 1 to point n. So is really a simple algorithm. Is really stable mathematically, so it's the one that's usually used and presented the first time. And you can see that's the actual entire algorithm. Everything else was just to draw the graph here. So take a list of points. If there is only one point, you return it, and if there is more than one, you call back that function with the two different ranges, and you do the linear interpolation between them. That's it. That's the Casteljau algorithm. Now, the Casteljau algorithm is well known and easy to use, but there is another way to compute a Bezier curve that you will probably encounter at some point, and it's to go through the Bernstein polynomials. So what are the Bernstein polynomial? It's a way of computing a bunch of functions depending on the degrees you want to use. So a Bernstein polynomial of degree n is defined as this function, and basically is depending of the number on the degree and the index, and it's also a function of t that goes between 0 and 1. And as you can see, k goes from 0 to n. So if you do a Bernstein polynomial of degree 3, you will have 4 different bases, basically. So let me show you what they are exactly. So that's the Bernstein basis. Just using that formula, the binomial coefficients you have here in front, that brackets, I'm using the comb functions from SciPy. And then if I just draw all of those, so for instance for degree 3, I will go degree 1 first, so you can see what happened. A degree 1 Bernstein will actually give you 2 polynomial, and then you will have the first one that starts at 0 at the value of 1 and end at the value 0 at 1, and the second one is just the opposite. And you could do as many of those, and you could see that the first one always starts at 1 and the last one always end at 1. And in between you have those curves. The particularity of the Bernstein basis is that at any point between 0 and 1, if you sum all of your bases, you actually have 1. So you see, the last one is the sum of my my 5 different curves, and it's equal to 1. What the Bernstein bases are used usually for is for approximation. Basically, without going too much in detail, because between 0 and 1, you can see you get a bunch of curves. So you could decide that you could try to give a multiplier for all of those different curves to try to mimic any functions you receive as an input. So what I have here is my green one is the functions I try to approximate using the Bernstein basis. And what I would do is that if I have degree 1, the best fit I can have is just a line. But as soon as I start to get a bit more degrees, I can actually get closer and closer to the actual function I'm trying to approximate. And now with a degree 13, meaning with 14 coefficients, I can approximate my curves the best as I can. Now, that's usually where you will encounter the Bernstein, but in our case, it can also be used to compute the Bezier curve. And how you compute a Bezier curve thanks to the Bernstein polynomials, you basically take all the Bernstein functions for the degrees of the Bezier curve you want to use. So if I want to do a cubic Bezier curve, I will have 4 points, meaning that I will have 4 different bases for the Bernstein. And I will just multiply my first point with my first base, my second point, my second base, third point, my third base, fourth point, fourth base. and sum all of them, and it will give me the Bezier curve. So let me write my Bezier function this way. So I take the degrees, and then I take my Bernstein basis, multiply it by the points, do it for each point, and sum the results. So that's my function. And you can see that if I just execute this function, I will have the same curves as the one I had before. So it's my 3 points that my curves, 4 points curves, and so on. And it's equal to the shape I have here. So that's the other way of computing the Bezier curve. And to show you that we are actually computing exactly the same things, what I will do is that I will use SymPy, which is the symbolic mathematic library inside of Python. And SymPy allows you to do math as in calculus, so you don't actually compute values. You could use letters and keep those letters. So what I would do is write the formula for a cubic Bezier using the Casteljau algorithm. So I do the linear interpolation for the first point and second and third and four, and then I interpolate those three, and then interpolate the final two. I expand all the mathematics, and I try to rearrange them in a certain order to have P1, P2, and P3 explicitly defined in my function. Now, I would do the same using the Bernstein formula, so using the binomial and then the exponent and the factors and multiply by the points. So that's the entire Bernstein base multiplied by the points. And I sum all those four, and again, I expand and I try to refactorize and collect the different values. And if I do this, what I can see is that, of course, it makes sense. You actually end up with the exact same formula, which is really proving that we were computing the same thing, just using different mean to reach them. What I would do here quickly, but it will be useful for later, don't worry, it doesn't make any sense at this point, is to say that if what we want to do most of the time is cubic Bezier, it also means that I don't need to use the Bernstein formula, or I don't need to use the Casteljau algorithm, because it's a cubic one, and I've just computed exactly what are the terms of that cubic. It will always be those same values. I don't need to go through the entire algorithm to do linear interpolation and all that kind of stuff. I could just use that formula and plug my P1, P2, P3, P4. Meaning that I can actually turn this into a matrix form, and that will be useful because often at later stage we will be using matrix form for a lot of different splines and different computations. So at least let's get used to this writing with the Bezier at this point. So what I do is that I define a matrix, and I've just reused, the terms that I have for all of my points here. So the point 1 is minus t cubed 3t squared minus 3t plus 1. So I do my minus 1, 3, minus 3, 1 in the first column. Point 2 is 3t cubed minus 6t squared, and so on and so on. So I write them in column. And now that I have that matrix, I can have the matrix for all the t's, t cubed, t squared, t, and 1. And I can also have the one for p1, p2, p3, p4. And basically what you do is that you write this as a matrix form. And just to prove you that this is exactly the same computation as this one, but written as a matrix, I could just execute the computation, and you could see that you end up with the exact same formula, right? One side note we could do about Bezier curve is what we call the rational Bezier curve. I don't have any example here because it's more just to know that it exists. If I need the mathematical formula at some point, I can grab and pick it from here. But basically what rational Bezier curve is the fact that you could say that you want to give more importance to a certain point than to another one. So you could say in the cubic one, the second point has two times more importance than the third one. And so you could give weights to each point to make the curves get closer to that point relative to another one. So the formula is basically the same as the normal one. You take your point, you multiply with the Bernstein basis, except that you also multiply it by the weight. So each point has a weight and a Bernstein base. And then you divide everything by the sum of all the weights multiplied by the Bernstein. So it's just to renormalize all the weights to make sure that everything keep a curve that goes between 0 and 1. So you need to divide by the sum of all the weights you injected here. And that's it, that's the formula. So basically it's the same as before, except that you multiply by the weights and then you redivide by all the weights and you have a rational Bezier curve. And now that we have one Bezier curve, usually what you will want to do is to actually make a spline with it, having several curves back to back, so you could define a real shape and keep going and keep working exactly as you do with keyframes. So what we will do is just having the system to compute the Bezier. You could see that at this time I know that I will be using Cubic Bezier, so I've used the matrix notation to compute the Bezier curve. So I just do the matrix, the multiply the point by the matrix and then the times, and that's it. So and then when I want to compute the Bezier spline, I would just take the first 4 points and do one Bezier with them, and then take the next 4 points and do the Bezier with them, and just reusing the first and last Bezier points so we can align them. So basically what you end up with is this. So you have two Bezier curve back to back. So that was my first, second, third, and 4, and then my first, second, third, and 4 points. And I'm sharing the point here in the 3 zeros for both Bezier. Now, you've seen that what I've done is I make the function for Cubic Bezier, and I said that will probably be the one we'll be using most of the time is cubic. And to be honest, everything else in this mathematical introduction will be about cubic spline, cubic anything, but it will be cubic every time. And so why do we focus so much on the cubic? It's because if we were doing only linear interpolation between all the points we have in our data, of course the first thing we could do is line our graph, and that's not exactly how you will want to interpolate your animation, right? If I go 1 degree higher and I go quadratic, what it means is a quadratic curve can actually bend in one direction all the time and has to only bend in that one. So if I have those 4 points now, I can have a nice curve that starts at my first point, reach the second, and then keep going from there with the same curvatures and go down. But then here I'm blocked because either I will have to go back up this direction and break my curve here, or having a curvature in the opposite direction. And anyway, I have a discontinuity here. So quadratic is not enough in our case here. And what we need to do is to go at least cubic, because cubic allows you to have 2 curves into your interpolations. So you can start with the one curvatures and end with the opposite one. And you can see that as soon as you go cubic now, I can have full continuity between all my lines, because I can curve up and then curve down, and curve up, and curve down. So now I'm able to interpolate my points. And I don't need to go in a higher degrees because the cubic is enough to actually curve both directions, and that's it. I won't go further in the number of degrees. And that covers the cubic, and then next time we will be going through a mid curve and see why we do them.